So in physics, the last lesson we did was really just a history lesson more than anything else. I linked in a couple of other videos that I thought you might find interesting. Some of you won't care at all, but some of you might find it interesting. Just about Kepler and Brahe and those types of things, and just I thought the videos kind of made the people seem kind of more real instead of just these people that live way back when, and we discuss them, but they don't actually seem like real people. But where we left off was we were talking about Newton, and so Kepler had already come up with his 3 laws of planetary motion, which you need to know. You need to know Kepler's 3 laws. It's just like Newton's 3 laws of motion. If you're going to study physics, you need to know that. Kepler, you need to know his 3 laws of planetary motion. That's actually really important. And so Kepler's laws led to people really wanting to figure out orbital dynamics and how is it that all this planetary motion works. And we had said that Haley was a scientist of the day, went and visited Newton at Cambridge, and he'd asked him the question, so what type of path would a planet take? And he said, oh, well, it's an ellipse. And he said, how do you know that for sure? And he said, well, I did the math a while ago, but lost my notes. He said, dude, go find your notes. And that led to one of the most famous scientific papers and books ever written. And so one of the reasons why Newton was successful in finding the law of universal gravitation when others couldn't was because Newton looked at gravity and this whole laws of attraction as being the same everywhere, whether you're on Earth or whether you're somewhere else. So he started looking at everyday objects and seeing how they interacted. And so he came up with what we now call Newton's law of universal gravitation, and it's up here. And so it says that the force of gravity between any 2 objects. So far, when we have found the force of gravity, we have talked about the force of gravity of a falling object, so something falling to Earth. But there is a force of gravitational attraction between any 2 objects. If you are sitting in front of a computer right now, which you must be if you're watching me, there is an attraction, a gravity attraction between you and that object. There is always a force of attraction, gravitational attraction between 2 objects. And so Newton said that the force of gravity, this is his law, and again it's on that PowerPoint that I uploaded, but he said the force of gravity is proportional to the product of the 2 masses. So whatever 2 things you're talking about, so you and the computer, it would be, I have to multiply your 2 masses together, and it's inversely proportional to the radius squared. So the distance between you and your computer right now, so that would be your R, we would square it. Now, he knew that there was another number that needed to be in that calculation, and so he represented it with a large letter G, and it's actually the universal gravitational constant is what it's called. So big G is the universal gravitational constant. It's just a constant. It's like pi or something like that. The thing was, Newton didn't know what that constant was. We do now because a guy named Cavendish actually discovered it, which I'll talk about a little bit later, and kind of how he did that, although we're not going to go in depth on how he did that because it was actually quite complicated. So we won't go into it too in depth, but I will briefly talk about it kind of later on in this section. But what was found eventually is that that universal gravitational constant is actually 6.67 times 10 to the negative 11th. Now the units are messed up. The units are newtons times meters squared divided by kilograms squared. And that is so that everything like kilograms squared is on the bottom. That will cancel out the kilograms that are up here. And meters squared is up here. That will cancel your meters squared here, leaving you with just newtons for force of gravity. So don't worry too much about the units, but the units are set up in such a way so that everything cancels out except for the newtons, because force of gravity should be measured in newtons. So I'm just going to do an example with you. It's on page 579. That's all we're going to do today. I'm going to assign you some questions to do. They shouldn't take long. They're all just using this formula right here. And that'll be it for today. Nice, easy day for a Monday. So a 65 kilogram astronaut. So mass 1, 65 kilograms. Is walking on the surface of the moon, and the moon has an average radius of 1.74 times 10 cubed kilometers. So radius is 1.74 times 10 cubed, but that's in kilometers. This is in kilograms. Okay. What is the weight of the astronomer? Now, one of the things we're going to need, we have mass 1, but we don't have mass 2. So what would be mass 2 would be the mass of the moon, because that's what we're figuring out, right? What is the weight? What is the force of gravity of the astronaut? So we need the mass of the moon, which we don't know. I'm going to upload, I have a table that gives the masses and the radii of all the planets, which normally in class I would just be handing you to use. By the way, you can use it on tests. It's not something I'm asking you to memorize. I'm never going to ask you to memorize what's the mass of the moon. That's crazy. So it is something that I will try to remember to attach today to this lesson, but you will need that in order to do it. If not, barring that, if I forget that, that's not an excuse not to do your homework, because it is at the back of the book. There's a table at the back of the book that has all of that in it. I would just have to find it. It's back here somewhere. I can't find it right off the top of my head, but there is a table somewhere. But I'll just upload that one anyway. I think I'll just take a photo of it. I think that's probably the easiest. So I'll just take a photo of it and upload it with this lesson. So mass 2, so just so you know, by the way, the mass of the moon is 7.35 times 10 to the 22nd kilograms. It's a moon. It's going to have a very large mass, right? And so we want to know what is the weight of the astronomer. So I'm looking for force of gravity. This really is just a matter of calculator work. There's nothing really to it. So force of gravity is G, which is 6.67 times 10 to the negative 11, times mass 1, which is 65, times mass 2, which is 7.35 times 10 to the 22nd. You really need to know how to deal with scientific notation on your calculator. I do recommend using brackets. Some calculators can handle it without it. Some really need the brackets. If you're not sure about your computer, if you're not sure about your calculator, default and use the brackets. Better to use them and not need them than to not use them and actually need them. Now that is going to be divided by, now, right now it's in kilometers. So we have to multiply this by 1,000 because there are 1,000 meters in a kilogram. So that is 1, 2, 3. So really all I have to do is add 3 onto my exponent, and that will automatically change it into meters. So it would be 1.74 times 10 to the 6 meters. You do have to do that though. So force of gravity, you can only have 3 significant figures, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so it works out to be 105 newtons. That's really all there is to it. So I will be uploading this video and the table that you're going to need that will have all the masses in it. Oh, there it is. It says see Appendix B, physical constants and data. So it does tell you where to go. It says Appendix B. I see Appendix A, C, Appendix B. Yeah, it is there. But I think the sheet I have has everything and more that you're going to need. So I'll upload that for you. So that's it for today. Pretty short, easy day. I hope the math doesn't stump you too bad, but it really is just that formula. All right? So we'll talk again tomorrow.